class, today we're going to be starting chapter 11, which is all about polynomials and rational functions. So section 11.1 covers zeros of polynomials. So let's take a look at that. So friendly reminder that a function is a quadratic function if f of x equals a squared plus bx plus c. Okay? And what we're doing is when we factor polynomials like this, we use the zero factor property to find the zeros of our quadratic equations. Now remember, these zeros are where our graph crosses the x-axis, so those are our x-intercepts. So remember, depending upon our polynomial, oh, that's a really messy coordinate plane. Depending on our polynomial, we can have 1, 0, or 2 y-intercepts. So let's go ahead and factor both of these and find their zeros. So for this first one, I want to find the factors of AC, which is negative 15, that add up to B. Factors of negative 15 would be negative 3 and 5, that add up to 2. So we're pretty good at this right now. We've been doing this for a few chapters. So I can write this as x plus 5 times x minus 3. And if I set each of these equal to 0, I get that my zeros are x equals positive 3 and negative 5. We're going to want to check our answers for those. Now, I was able to use a shortcut because my leading coefficient in this case is 1. But for this second example, we're not going to be able to do that because our leading coefficient is 3. Negative 3. The first thing I need to do is factor out that negative, right? We don't like negative coefficients. So I'm going to have f of x equals negative 3x squared plus 2x minus 1. So now I need to find the factors of AC, which is negative 3, that add up to B, which is 2. Some factors of negative 3 that add up to 2 are going to be 3 and negative 1. And now I need to rewrite this middle term so I can factor by grouping. So I have f of x equals negative 3x squared plus 3x minus x minus 1. We're going to factor by grouping. So I get f of x equals negative 3x times x plus 1 and negative 1 times x plus 1. So I'm going to have negative 3x minus 1 and x plus 1. So I will set each of these equal to 0 and solve for my x's. So that gives me x is 1/3. X plus 1 gives me x is a negative 1. So my x-intercepts are negative 1 and 1/3. Remember that you need to check these into your solution to determine if you have 2, 1, or no x-intercepts. Now, a polynomial, so a quadratic is a degree 2 polynomial, and a polynomial function of degree n is defined by f of x such that there are coefficients, and I have x to the n, x to the n plus 1, x and a constant, right? If we just add a number without a variable, that's a constant. And this is for real numbers, an minus 1, a1, where, a0 doesn't equal 0, and n is a whole number. And what we can do is use division to break these polynomials apart, right? We learned how to factor quadratics, degree 2. Now we're going to learn how to factor specifically cubics, so something a little bit bigger. So if I have a function, I can break it apart into 2 factors, but there's going to be a remainder, right? When we divide, we see a lot of remainders, okay? But as long as our polynomial, there is a way to break these apart with a remainder. And if r equals 0, r of x equals 0, then that means that these are perfect factors. So let's take a look at how we're going to use this division algorithm. So let's divide the following polynomial. We know how to divide. We know that I need to take x minus 4, 3x squared minus 2x squared plus 0x. Remember, this doesn't have an x term, so I need to put in a placeholder, because in order for long division to work, this is what we're doing, we're using long division, I need to have a placeholder. So I'm going to go ahead and take, this is an x cube. I want to know, what do I multiply x by to get 3x cubed? That's going to be 3x squared. So that gives me 3x cubed minus 12x squared, and I subtract this. My first two terms cancel. I have negative 2x squared minus a negative 12x. Well, two negatives make a positive. So I have 10x squared, and then I pull down my 0x. Now I want to know, what do I multiply x by to make it look like 10x squared? The answer to that is just going to be 10x. So I have 10x squared minus 40x. I subtract this. That gives me 40x minus 150. Now I say, okay, what do I multiply x by to make it look like 40x? The answer is going to be 40. So I have 40 times x is 40x. 40 times negative 4 is negative 120. I subtract these from each other, and I'm left with negative 30. So how did this break down? So now I know that my original function, this top one, right, it could be written as x minus 4 times 3x squared plus 10x plus 40 plus negative 30. This right here is my remainder, and these right here are my factors. And if I wanted to, I could factor this even more, right? This is a degree 2 quadratic, and we know how to factor those apart even further. Well, what if I told you there was a shortcut to long division? The shortcut to long division is called synthetic division, and this only works when we're given a polynomial in the form x minus k. So let's do the same problem, but I'm going to show you how to use synthetic division. It's synthetic because we are only working with the coefficients. So here I'm going to take my k, which is 4, and I'm going to take our coefficients. So I've got 3, negative 2, remember we have 0x here, so not forgetting my 0, and negative 50. And the way synthetic division works is this. I'm going to pull down my first term. I'm going to take 4 times 3, that gives me 12. I'm going to take negative 2 plus 12, that gives me 10. I'm going to take 4 times 10, which is 40. I add this column together, right? I'm adding these. That gives me 40. 4 times 40 is 120. Negative 50 plus 120 is negative 30. So this was a degree 3. Then this is going to be a degree 2 because we were dividing. A degree 1, our constant, and then this right here is my remainder. Doesn't that look really familiar? That we would get 3x plus 40, 10x plus 40 as a factor, and this was our remainder. So I still have that this original function, up here is equal to x minus 4, right? It had been the term x minus k, that's why our k was just 4, times 3x squared plus 10x plus 40 with a remainder of negative 30, so it'd be plus a negative 30. So let's practice using synthetic division to solve the following, and we're going to rewrite our answers in this form, okay? Now remember this x plus 1 that we're dividing by, it needs to be in the form of x minus k, okay? So I can rewrite this as x minus -1. So this -1 right here is my k. So I'm going to have my k, and I'm going to take my coefficients. So I have a coefficient of 1, 3, 11, and 9. I'm going to go ahead and pull down this factor of 1. -1 times 1 gives me -1. 3 plus -1 is 2. -1 times 2 is -2. 11 plus -2 is 9. -1 times 9 is -9. 9 minus 9 is 0. Okay, this is our remainder. That means that these are perfect factors. I have f of x, which is this function here, equals x plus 1 times 1x squared plus 2x plus 9. And then there's no remainder. I didn't even finish spelling that word. There's no remainder. All right, another example. Remember, our denominator needs to look like x minus k. So I'm going to rewrite x plus 2 as x minus -2. So that means my k is -2. I'm going to have -2. And then my factors of 5, my coefficients of 5, -6, -28, and 2. I'm going to go ahead and pull down this 5. -2 times 5 is -10. -6 plus -10 is -16. -2 times -16 is 32. And -28 plus 32 is 4. -2 times 4 is -8. And -2 plus -8 is -10. So this is my function, 5x squared, remember it's just 1 degree less, minus 16x plus 4, and then this is my remainder right here. So I can rewrite my function, remembering that this was our function. My function is now x plus 2, our denominator, times 5x squared minus 16x plus 4 minus 10. Or you could write plus a -10 if you prefer. Here is a visual of an example that I found online in case you should get lost. So you can use this as a reference.